Hello everyone. So in this video we are going to discuss about the topic which is aromatic hydrocarbons. Previously we are done with the pure hydrocarbons in which we understood about alkane, alkene and alkyne and their various reactions, preparations, characteristics, uses and whatnot. All of this is present in the previous video, so please be sure to watch that video in order to make your concepts clearer when we are watching this video as well. So let's just understand what a benzene is. If you just talk about benzene, it is an aromatic compound. Now, many people ask what is meant by an aromatic hydrocarbon. What is an aromatic hydrocarbon in general? An aromatic hydrocarbon is such a hydrocarbon which is having a unsaturation, a hydrocarbon which is having unsaturation in a cyclic ring. Such type of hydrocarbon is known as aromatic hydrocarbon. The simplest aromatic hydrocarbon which is found is benzene. We just talk about its history. It was, discovered by Michael Faraday when he performed a destructive distillation of vegetable oil, and he found a benzene. And 20 years later, Hoffman found that through destructive distillation of coal tar, we can actually create benzene as well. And some common characteristics of benzene is that it is having its boiling point as 80 centigrade. It generally exists in liquid form at room temperature, and its molecular mass is 78.1, which is obtained through vapor density method. Now, when it comes to its when it comes to its common properties, it is having sp2 hybridized orbitals. sp2 hybridized orbitals. We need to understand what benzene is essentially. Essentially, benzene is a cyclic, regular, hexagonal. It's a cyclic, regular, hexagonal uh, ring which is having three double bonds. This is something really important to consider, which alternate three single bonds. This is something really important to understand. Whenever we are having alright, whenever we are having a benzene structure, if you just understand the benzene structure, benzene is like this. Let me just try to make it more clear. Benzene is like this. This is the structure of benzene, such that there are, this is, let's say, the benzene ring, the hexagonal ring, and there are alternate pi bonds. One double bond here, and then a single bond, and then another double bond, and a single bond, and then another double bond. So this is how the structure of benzene is drawn. Now, if we just look into the the molecular structure, we just find over here that benzene as sp2 hybridized orbitals. sp2 hybridized orbitals. For example, if it is, let's say carbon is present over here, and that carbon in benzene, I'm just going to take this carbon out. I'm going to take this carbon out and try to draw the structure. These are the 4 electrons of carbon, right? So uh, two of the electrons which are present in the S and P orbital they basically undergo hybridization to form sp2 hybridized orbitals. So in general there are two hybridized orbitals formed. Two hybridized, sorry, it's not going to be two hybridized orbitals, there will be three hybridized orbitals because it is sp2, right? So three hybridized orbitals, this is sp2, this is sp2, this is sp2, and one orbital which is 2pz orbital which forms a pi bond. So one sp hybridized orbital combines with hydrogen, another combines with another hydrogen, other sorry, one combines with hydrogen, other one with combines with another carbon, and another sp2 hybridized orbital combines in another carbon. And there's 2pz orbital which is parallel, and that parallel orbital basically forms a pi bond. So if you just take this structure out, we will basically find one carbon here, one carbon here as well at the edges. So this at this point there would be an sp2 bond. Here there would be an sp2 bond, and it is having a hydrogen attached to it, and that bond would be sp2s bond. And essentially we are going to have essentially we are going to have essentially we are going to have the pi bonds which would be overlapping it. It's better to show the 3D structure. The pi bonds would be like this. This is one pi bond, another pi bond, and in that way all of the other pi bonds. So basically, if you just take it and give it a lateral view, we will basically see that the upper side of the benzene ring is covered with the pi electrons. It's covered with pi electrons from upside. So, and down towards the benzene ring there is a down electrons are present on downward side as well. So essentially what I really mean to say is benzene structure is more of a sandwich structure, which means that above it there are pi electrons, below it there is a pi electron cloud, and that basically makes it pretty stable. There are other factors for its stability as well. Sandwich structure is one of the factors. So, some other common characteristics about benzene is that benzene is higher. Benzene is benzene is having the bond angle which is 120 degree. The carbon to carbon bond is 1.4 angstrom. Carbon to hydrogen bond is 1.09 angstrom. These are some important factors. Now, let's just understand one more thing. That within benzene, within benzene, we are having some characteristics of benzene, such that let's say if I take this benzene ring again, benzene can only form one monosubstituted product. It can only form one monosubstituted product, such that if I just take this benzene would basically have one monosubstituted product. So, for example, if I take chlorine and add it to the benzene, cause an addition reaction, not an addition reaction essentially, but let's say a substitution reaction. So what will actually happen is the monosubstituted product would be can the monosubstituted product can attach to any side of the benzene. It can attach here, it can attach here, here, here. So essentially it has only one monosubstituted product. Let's say the monosubstituted substituted product is uh, can attach anywhere, due to which whatever side the monosubstituted product is having the substituent attached to will be the point of origin of the other substituents. So in that way, the monosubstituted product is only one. But if you talk about di-substituted product, for example, let's say I take a chlorobenzene. I take a chlorobenzene, right? I take a chlorobenzene over here, and then what I'm going to do is I'm going to add a nitro group with it. I'm going to add a nitro group with it. So when I'm going to add a nitro group with it, there are three possibilities for the nitro group to attach. There are three possibilities of forming a di-substituted product. Either the nitro group can attach here, or it can attach here, or it can attach here. These positions are named as ortho position, which is nearest from the chlorine. We are taking chlorine as a reference. Meta position and para position. So in that way, from the first by taking the first substituent as a reference, the second substituent will have three uh, positions, which is ortho, meta, para, due to which we say that there are three di-substituted products for benzene. Now let's just understand few things, that how did we came to understand the structure of benzene at such a young age. So basically, uh, scientists in the early 1900s were unable to identify that what benzene structure is, because at that point it was benzene essentially has it has the capability to undergo addition reaction, as well as it has the capability to undergo substitution reaction. And as I told, it is only one monosubstituted product and three disubstituted product. It had characteristics of an alkane, it had characteristics of an alkene, alkyne, as well as cycloalkanes as well. So there was a scientist named as KQ. What KQ did was, KQ utilized his intelligence in order to find what the structure of benzene is. He deduced that if benzene is monosubstituted and it is having three disubstituted products, then at that point it's 100% going to form a cyclic hexagonal ring. Cyclic hexagonal ring. Sorry, it's hexagonal ring. It's 100% sure that it's going to form a cyclic hexagonal ring logically. And then what he did was he took the benzene, and then he reacted benzene with chlorine. He took benzene and he reacted benzene with halogens. He took halogens in the presence of UV lights. At that point, when he took the benzene in the presence of UV light, he basically found that there was formation of a hexachlorocyclohexane. Hexachlorocyclohexane. Cyclohexane. So what it actually meant was that benzene is forming hexachlorocyclohexane because it is having three double bonds in it. Three double bonds which alternate with it. And on the basis of this deduction, he basically found out the found out two structures for benzene, which were named as the Kekulé structures. Um, one structure like this. This was one of the structures, and second structure like this. So these were the two structures which he named as Kekulé structure. Now after that, basically there was another scientist named as Daver. Basically Daver did was Daver also purposed some uh, structures for benzene, but those structures were pretty unstable because they were having some long double bonds within the benzene ring, which made it pretty unstable. For example, if it is, let's say, C1 and it is C4, then this was a structure formed such that all of the pi bonds were parallel to each other, which essentially makes the middle bond pretty longer. The bond distance is higher in the middle bond, due to which the structure became very unstable. In that way, he basically gave um, you know three structures. He basically gave three structure. For example, this was one of the structures. Let me just draw one more. I don't know if it is. I don't know. Oops. Let me just draw it once again. Yes, and this structure. So if you just talk about diverse structures, all of these structures were unstable, and that's the reason that whenever we are going to calculate the resonance, diverse structure are considered as a minor structures because they exist for a very short period of time because of their instability. All of these are parts of the resonance scheme, but KQ structures are major ones which are mostly viewed, and diverse structures are minor ones which are less viewed. So if we just take a sum up of all these structures, we take a sum up of all these structures, and make it summarized in a single diagram. We basically draw this. We draw a circle in the middle which shows that this is a benzene ring having the electron cloud which is revolving in it, and that electron cloud basically is the reason for its stability. This pi electron cloud is responsible for the diffused electron cloud or the delocalized electron cloud. This pi electron cloud basically is the diffused or delocalized electron cloud that is responsible for the high stability of benzene. So there were certain experiments conducted as well in the early centuries where people, scientists basically took cyclohexatriene, compared the values of cyclohexatriene with cyclohexadiene, and benzene. What the scientists did was they basically found this heat of hydrogenation of cyclohexene first. Cyclohexene. They first found the heat of cyclohexene, heat of hydrogenation, and what they did was they found that the heat of hydrogenation was 100 kilojoule per mole. Now, if you just put it pretty simple, when this was a heat when there was a double bond in the cyclohexane, but when I'm going to multiply it by 3, it can hypothetically be considered as cyclohexatriene. It can hypothetically be considered as cyclohexatriene, which is basically 360 kilojoule per mole. But when we actually calculated the heat of hydrogenation of benzene, it was found that the heat of hydrogenation is 208 kilojoule per mole. It was such a huge difference, 208 kilojoule per mole and 360 kilojoule per mole, which basically defines the fact that over here there is a huge difference in the stability of benzene and the stability of cyclohexatriene, which means that benzene has extra stability as compared to cyclohexatriene, which was a hypothetical compound. It does not exist actually. That and that extra stability is calculated as the resonance energy. Uh, th- that's resonance energy is 152 kilojoule per mole or 36 kilocalorie per mole, and that basically is a resonance energy which happens due to resonance. Now, what is resonance? We are going to study it right now. These are the structures which Dever and Kepkus have, for purpose. So, over here, whenever there is possibility of different pairing schemes of valence electrons in an atom, then at that point that atom is supposed to be in resonance. So what resonance is, essentially resonance is the possibility of different electron pairs, possibility of different pairing schemes of valence electrons in an atom. So there are different pairing schemes. We don't need to understand that, but what we are going to do is, what we're going to do is we are going to consider this resonance, that there are five resonance structures. The more number of resonance structure are there in a compound, the more stable the compound is. The five resonance structures are these: Kekulé structure and diverse structure. Out of this, diverse structures are minor ones and Kekulé structure are major ones. So when resonance happens, these structure vary with each other, such that there is a headed arrow. This double headed arrow indicates that uh, these structures are in equilibrium with each other. They are basically varying with each other so fast that we cannot even see them. So essentially, all of these five structures are making benzene a resonant hybrid, which means if you just look into benzene structure, I mean like look into the benzene ring, essentially we do not find, we actually don't find this, we don't find this, we don't find this, we don't find this. What we actually find is, we find this. What does this circle indicate? The circle basically indicates the diffused electron cloud which is present in the middle, which is the result of all of these five resonance structures. So this is the entire thing about resonant hybrid. Alright. So moving forward, there are certain methods through which we can prepare um, benzene. Benzene can be prepared in such a manner that, over here, let's say I take cyclohexane and I perform dehydrogenation of cyclohexane. For example, I take cyclohexane and I perform dehydrogenation, and the catalyst is platinum at 250 centigrade. I will get benzene. Second method is I take acetylene at 70 centigrade. In the presence of organonickel catalyst, it will form benzene. Now I can also make it from alkanes. What I do is I take N-hexane, use the catalyst chromium oxide, aluminum oxide, silicon oxide at 500 centigrade, I get benzene. N-heptane with chromium oxide, aluminum oxide, silicon oxide at the same temperature 500 centigrade, and I will get toluene. If I'm using N-hexane for making benzene, it will form benzene. If I'm using N-heptane, it will form toluene because of the 7 number of carbon atoms. Alright, let's move forward. Over here, when we are going to, there are some laboratory methods as well. We can prepare benzene through laboratory methods. Number one laboratory method which we have is the distillation of phenol. We distill phenol with zinc dust, due to which we get benzene. When we take sodium benzoate and react it with soda lime, caustic soda lime in the presence of quicklime, then at that point we get benzene and sodium carbonate. Likewise, benzene sulfonic acid, when we are going to take benzene sulfonic acid and hydrolyze it in the presence of a dilute HCl, or in the presence of superheated steam, then at that point I can get benzene. And another method is, this is the most important one, it is the Furtz, sorry, it's not Furtz, the Wurtz fittig reaction. Wurtz fittig reaction. Wurtz fittig reaction. So this is Wurtz fittig reaction. Wurtz fittig reaction. What a Wurtz fittig reaction is? We take a bromobenzene and react it with ethyl bromide in the presence of an anhydrous ether solvent. Then at that point we will get ethyl benzene and sodium bromide. This method is important because it is industrially used to prepare benzene, ethyl benzene particularly. Now let's talk about some reactions. So we have to understood that benzene is a highly stable molecule. Benzene is highly stable, but it is reactive as well. It is highly stable, but it is reactive as well. How is this possible? That's because of the resonance structure. So, um, because of benzene's unique capability to be stable, it it has substitution reaction which readily happen in benzene. And what type of substitution reaction do happen? We need to understand it conceptually. Benzene has a pi electron cloud, a diffuse electron cloud, delocalized electron cloud, and that delocalized electron cloud needs to the delocalized electron cloud is negatively charged, which means that benzene is a nucleophile. And what type of nucleophile is it? It's a strong nucleophile because the pi electron cloud is present inside the benzene ring, due to which it's a strong nucleophile. Due to which we need a strong electrophile in order to perform the substitution reaction in benzene. So it is an electrophilic substitution reaction in which we need a strong electrophile. Second type of reaction that benzene undergoes is addition reaction. Addition reaction is pretty hard to do, but there are some methods in which we provide harsh conditions and undergo cause addition reaction. And the third is oxidation reaction. Benzene can undergo oxidation reaction, but again that oxidation reaction again requires harsh conditions. So let's just look into all of these phenomena. First, we need to understand the mechanism of substitution electrophilic reaction. Mechanism of electrophilic substitution reaction is in such a manner that there are three steps involved in the formation of a substituted benzene. Number one step is Number one step of forming a substituted benzene is that I take a strong electrophile. In order to form, sorry, in order to form, in order to cause the substitution of benzene, I'm going to basically take a strong electrophile. And how can I prepare a strong electrophile? A strong electrophile can be prepared. A strong electrophile. At first stage, we need to create a strong nucleophile. So the first stage is creation of strong nucleophile. So for the strong nucleophile, what we'll actually do is we'll actually take a Lewis acid. We take a Lewis acid. For example, I take iron chloride, and I react iron chloride for let's say I react iron chloride with halogen. Then at that point, it's going to give me this is the reaction mechanism for halogenation, but we are going to look into other mechanisms as well. So anyways, tetrahaloferritine, this is tetrahaloferritine, and it will give me a strong electrophile, which is the chloroniamine. That chloroniamine, what actually it will do is it will go with the electrophile. This chloroniamine is a strong electrophile, and that strong electrophile then will go into the benzene ring and attach to it. At that point, the benzene ring would basically have the electrophile attached to it. That's it. And at that point, because the electrophile is attached to it, this would be named as phenoniamine. phenonium ion. And that phenonium ion, what actually will happen is that phenonium ion will release the proton, will release the hydrogen atom, and that hydrogen atom will go back to the catalyst to regenerate the catalyst. Due to which, let's say, let's make it pretty contextual. I take this E and H, and then I take the catalyst back. This is the catalyst. I mean, this was the product. This was something left. What actually will happen is the H will attract chloride ion from tetrahaloferrate, due to which it will form HCl, and the regenerated catalyst iron chloride and the substituted benzene. So this is the entire mechanism. So now we are going to look into the deep understanding of the mechanism. This is the entire reaction that I explained over here. This is summarized in here. So this is halogenation. What we actually do is we first make a strong electrophile, which is done in this step, and then I take attach it with benzene, due to which it forms phenonium ion. Phenonium ions then releases hydroproton. Proton combines with iron tetrachloride to give HCl and iron trichloride. That's his halogenation reaction. And in halogenation reaction, we use Lewis acid catalyst. Now we have nitration. In nitration, what we actually use is we use nitric acid and we use sulfuric acid in equal quantity, such that both of them will have a mixture ratio of 1:1, and the temperature is around 50 to 55 centigrade. What actually happens is when nitric acid reacts with sulfuric acid, it produces nitronium ions, sulfate ions, and hydronium ions. So let's just understand that what is the role of nitronium in this. Nitronium is basically the strong electrophile. That's the major electrophile which is going to attack on benzene. It will attack on benzene and form the phenonium ion. The phenonium ion will now basically take hydrogen. The phenonium ion will give hydrogen to HSO4, due to which it will form H2SO4, which is the catalyst that is regenerated. That's all about it. Now, an important thing to consider here is that the formation of phenonium ion is in equilibrium. It is in reversible reaction. And now let's just move on to sulfonation. Sulfonation is also having the formation of phenonium ion in equilibrium, such that in a reversible reaction. So let's just look into it. So for performing sulfonation of benzene, what we actually do is we either take fuming sulfuric acid. Fuming sulfuric acid is H2SO4 plus sulfur trioxide. This is fuming sulfuric acid. And second type of acid is concentrated sulfuric acid. Concentrated sulfuric acid is simply H2SO4 in concentrated form. We are going to take concentrated sulfuric acid for the main mechanism, because the electrophile essentially is sulfur trioxide. First, if we take concentrated sulfuric acid, we need a temperature of 80 centigrade, and at that point we are going to form hydronium ion, sulfur trioxide, which is a major electrophile, and hydrogen sulfate. What actually happens is sulfur trioxide attaches with benzene to form benzene hydrogen sulfonic acid, benzene sulfonic acid. And then benzene sulfur, what actually happens is the phenonium ion will give its hydrogen to HSO4 to form H2SO4, and that um, and the sulfate, the benzene sulfonic acid, which is lacking one proton, would take one proton from hydronium ion and will produce benzene sulfonic acid. Now, if it is in the case of sulfur trioxide, then sulfur trioxide, if instead of let's say instead of two H2SO4, there is sulfur trioxide. Then in this case there would be formation of sulfur trioxide and HSO4, and instead of protonium ion there would be a proton. Now then what will actually happen is that sulfur trioxide will again form phenonium ion. Phenonium ion will take will give its proton to HSO4, due to which H2SO4 would be formed, and then this proton would directly attach with sulfur trioxide in order to produce sul sulfur benzene sulfonic acid. Now, in both of these conditions, the phenonium ions exist in equilibrium, are in a reversible reaction. Alright, now there is an important topic which is the Friedrich-Crafts alkylation, Friedrich-Crafts reaction. There are two Friedrich-Crafts reactions. Friedrich-Crafts basically was a scientist who used a very interesting method to cause the alkylation or acylation of benzene. Alkylation, both of the methods involve the use of a Lewis acid, which is aluminum chloride. Essentially, it can be aluminum chloride, it can be aluminum bromide, but what we are going to do is we are going to utilize aluminum chloride. Uh, on the basis of this, we are having two major reactions. We have alkylation and acylation. Let's look into both of them. First, we need to understand how alkylation happens. Alkylation happens in such a manner that basically we take the aluminum chloride, the Lewis acid, and we take alkyl halide in alkylation. When both of them will react, they will form an alkyonium ion, and aluminum tetrachloride. Sorry, let me just mark it as chloride ion. Right? Just erase all of this. The alkyl chloride, when reacted with aluminum chloride, will form the alkyonium ion and aluminum tetrachloride. This is the first step, formation of strong electrophile. Then this positively charged alkyl, we can uh, call it as a carbocation. This positively charged carbocation will then attach with benzene to form phenonium ion, and that phenonium ion, when will attach with aluminum tetrachloride, will essentially form the attach with the aluminum tetrachloride. When it will take the hydrogen, then at that point it will form HCl, aluminum trichloride, and alkyl benzene. Now there's something different with acyl group. Acyl group is pretty similar. It's like acyl. First, we need to understand what an acyl group is. Acyl group is this. This is an acyl group. Now we need to understand what we actually use for this. Again, we are going to use Lewis acid as the common thing, aluminum chloride. I take what I'll actually do is I will take aluminum chloride and I will use acyl halide. Acyl halide. Acyl halide. I'm going to, let's say, add chlorine over here. Acyl halide. So when I am going to react them, what I'll actually get is I will get aluminum tetrachloride and I will get the acyl group, which is positively charged. This positively charged acyl group can also be known as acylonium. Now what I'll do is I'll take this acyl group, positively charged acyl group, and that acyl group would now be reacting. That acyl group will now be combining with benzene to form phenonium ion. That phenonium ion will now, uh, you know, that phenonium ion will now lose one, give its hydrogen to aluminum tetrachloride, due to which HCl and aluminum trichloride will be formed. So that's all about it. This compound which would be formed is known as acetophenone. Acetophenone. Alright. These are some of the reactions which are involve electrophilic substitution. Now let's discuss some addition reactions. Addition reactions involves number one, hydrogenation. This is a hydrogenation reaction where we either take nickel at 200 centigrade or we take platinum in a weak acid in a weak acid such as acetic acid. So we take platinum in a weak acid like acetic acid or nickel at 200 centigrade. Second method is the halogenation. The second reaction is halogenation of benzene. We can cause halogenation of benzene in the presence of UV light, which forms hexabromo cyclohexane. And then we have the reaction oxidation of benzene, catalytic oxidation of benzene, which is done with the help of vanadium pentoxide at 450 centigrade. That basically produces malic anhydride, and that's also the commercial process for formation of malic anhydride. And malic anhydride again, when it is given water, it will decompose into malic acid. Now let's discuss another one, ozonolysis. Ozonolysis basically is a process when we take ozone. It's not actually oxygen. These are three ozone molecules which basically react with benzene in order to produce benzene trioxide. And that benzene trioxide, triozonide, not trioxide but benzene triozonide. That benzene triozonide, when it is given zinc and water, it will form glyoxal. And right after this, we have another reaction which is known as combustion. Combustion is pretty simple. When we burn benzene ring in the presence of excess of oxygen, we basically get carbon dioxide and water. That's all about combustion. This is another reaction. This is side chain oxidation. Side chain oxidation is pretty important because side chain oxidation will have potassium permanganate. We'll use an oxidizing agent, potassium permanganate, which will only oxidize the side chain but will not affect the benzene ring at all, such that the side chain will be oxidized and form carboxylic acid. Now, no matter what is the length of the alkyl chain, or no matter what is the length of alkyl chain, the number of carboxylic acids which would be formed is 1. For example, instead of CH3, I'm having CH2, CH2, CH3. If I'm, let's say, having 4 carbon atoms attached to benzene. So, will it give me 4 carboxylic acids? It will not give me 4 carboxylic acids. It will only give me 1 carboxylic acid and give me 3 carbon dioxide molecules. So this is a thing that comes with potassium permanganate oxide. And when the reaction happens, the potassium permanganate oxide basically transfers its color from purple to colorless. What does this mean? This this can actually be helpful for scientists to work and basically find or identify alkyl benzene. It can be a test for identification of alkyl benzene. Alkyl benzenes can be identified with the help of side chain oxidation. All right. So after this, we are having another topic, which is the directing groups. Now, directing groups are pretty simple. Directing groups are not that difficult. What actually happens is, we've known that let's say if this is let's say if I take again, this is benzene and I combine it with chlorine, it will basically give me chlorobenzene, right? It will give me chlorobenzene. So this is a mono-substituted product. This is a mono-substituted product. Now, for suppose this is a mono-substituted product. So this mono-substituted product forms the chlorobenzene. But let's say if I want to add one more group, let's say I want to add nitro group in it, then it will basically produce this. It will produce a chloro group and it will direct the first substituent will direct the position of the second substituent, right? So the second substituent is nitro group, that would be directed either on the ortho position or it will be directed over the para position, and that is basically an effect which is known as the orienting effect. Orienting effect is something pretty crucial to understand because uh, you know with the help of orienting effect, actually scientists previously believed that statistically there are three dye-substituted products, right? There are three dye-substituted products. Uh, either the dye-substituted product is ortho, or the product is meta, or the product is para. So there should be 20% para, there should be 40% meta, and 40% ortho. But when they did experiments, they found something really different. As the one in this, when they used chlorine, when they added nitro group to chlorobenzene, then they basically saw that there is addition of nitro group either on the orthocarbon or on the paracarbon. Likewise, if they used a nitrobenzene and they reacted it with chlorine, then at that point there would not be the formation of ortho or para chloronitrobenzene. There would be formation of a meta chloronitrobenzene. Meta chloronitrobenzene. So this is pretty strange. This can be explicitly explained in two ways. There are two types of groups. There are two, two types of directing groups or orienting groups. Directing, two types of directing groups. One group which I'm going to write over here is the ortho para directing group, and the other group is meta directing group. Alright, so when it comes to ortho para directing group, it is the electron rich group. It is electron rich group. And because it is electron rich group, it donates electron to the benzene ring, due to which it is also known as electron donating group, EDG, electron donating group. And because it donates electron to the benzene ring, it makes the benzene ring more reactive. And due to this reason, we call this group as activating group, because it activates the benzene ring. Activating group. So if you just take examples of ortho directing groups, there are many ortho directing groups. Number one ortho directing group which I'm going to write over here is this. There are many ortho. It can be halogens. Halogens are ortho para directing group, but they are deactivators for some reason. There's a specific reason. Amine groups, acyl groups, alkyl groups are all of the ortho para directing groups. And you might notice one important thing, that all of them are having lone pairs, or even not all of them, but some of them are having lone pairs. So whenever there's a lone pair in the adjacent atom to the benzene, then it means that that is an ortho para directing group. Another type of directing group is meta directing group. Meta directing group is the electron deficit group. We can also write electron rich or electron deficit in terms of nucleophile and electrophile. I can write over here nucleophile. I can write over here electrophile. Electrophile. Alright. So meta-dieting group is electron deficit group. It is an electrophile whenever there is an electrophile attached. Not essentially the entire electrophile, but the atom which is directly attached to carbon in the benzene. When that atom is electrophile, at that point, this is a meta-dieting group. It is an electron withdrawing group, such that it you know attracts the electron towards it, withdraws the electron from the benzene ring into its structure, and due to this reason, it is less reactive and it is a deactivating group. It is a deactivating group. It is a less activating group. It is a deactivating group. Now, it is a deactivating group. It is a less reactive group. It is a deactivating group, and all meta-directing groups are deactivating groups. But some of the ortho-para-directing groups are deactivating as well. Halogens are deactivators, while the rest of them are activators. Now we take example of meta-directing groups. Meta-directing group has example of aldehyde, example of ketone. We have carboxylic acid, cyanide, sulfonic acid group. We have uh, we have we have the uh, we have the sulfide. We have the sulfonic acid group. We have the nitrile group, carboxylic acid group, ketone group. There is the nitro group, and there is so these are some examples. Also, OH group is also example of the ortho-para-directing group. These are examples of meta-directing groups. Aldehyde, ketone, carboxylic acid, nitrile, sulfonic acid, nitro. All of these are meta-directing groups. And we can also recognize meta-directing groups by an important factor. Whenever the adjacent atom, let's say if I draw this benzene ring, I draw this benzene ring, I draw this benzene ring, and I draw the entire structure of nitrogen, nitro group. Now, if you just see, the nitro group is in such a manner that it is having partial negative charge on oxygen and partial positive charge on nitrogen. Now, because of electronegativity difference, oxygen is more electronegative than nitrogen. Nitrogen becomes partially positive, and due to this reason, this atom which is adjacent to the benzene would be the meta-dieting group because it is partially positive. It is an electrophile, and because it is an electrophile, it is an electron withdrawing group and acts as a meta-dieting group. So whenever we are going to have a partially positive charge on the adjacent atom to the carbon in the benzene ring, then it simply means that it's a meta-dieting group. So this is all about it. It's the simple concept, and on the basis of this meta-dieting and ortho-dieting group, we have the formation of trinitrotoluene. We have the formation of uh, we have the formation of trinitrophenol, also known as picric acid, such that trinitrotoluene is made in such a manner we take toluene And since toluene basically has got a CH3 group over here, and when it is combined with three nitrogen atoms, three nitric acid molecules, such that in a very concentrated nitric acid, then it is going to form trinitrotoluene, which is an explosive essentially used in atomic bombs. And trinitrophenol, that basically happened. Now, why did it happen? Because methyl group itself is a is an activating group that caused the activation of the ring and allowed the nitric acid to combine together to form trinitrotoluene. Likewise, we try nitrophenol such that we take, let's say, picric acid. In picric acid, we basically have a phenol, and that phenol combines with the which concentrated reacts with the concentrated nitric acid to produce the nitro group. So, in that point, the phenol at that point at that point it is going to produce trinitrophenol when the nitric acid is extremely concentrated, and that's what we're forming. That would be named as trinitrophenol, also known as picric acid, which is done because hydroxyl group is activating group is orthopara directing group, due to which it will direct nitro group to orthopara positions, and it will direct a nitro group to the ortho and para positions, and this would be basically forming trinitrophenol picric acid. So that's all about it. Now there are some things which we need to learn. Benzene has got two major structures. Number one is monocyclic structure, and number two is polycyclic structure. Whenever we talk about monocyclic structures, they are having one benzene ring. For example, toluene. This is, let's say, benzene ring, and methyl group is attached to it. It will be named as toluene. When benzene ring has OH attached to it, it would be named as phenol. When it is having amine group attached to it, it would be aniline. When carboxyl group is attached, it is known as benzoic acid. When when benzene will have aldehyde attached to it, it would be named as benzaldehyde. So these are some common names. Now there are polycyclic aromatic hydrocarbons or polycyclic benzenes as well. Polycyclic benzenes can be further divided into two types. Number one is the isolated rings, isolated benzene, isolated aromatic hydrocarbons, and the fused hydrocarbons. Isolated hydrocarbons are these: biphenyl benzene, such such that it is having two benzene rings which are isolated with each other, and there is diphenyl methane, which is again isolated by a methylene group. And then we have the fused benzene rings, such that these benzene rings are connected with each other continuously. For example, when two fused benzene rings are there, this is known as naphthalene. When three fused benzene rings are there, there is anthracene. When the benzene rings are in such a manner that there are two benzene rings fused, and then there is another benzene ring on top of that in this structure, that would be phenanthroline. These are some important points to consider. That's all about this video, or hopefully we'll meet again in another video. Thank you.